Hello everybody, this is Luboš Pirkl from CFD Support. I am here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello Luboš, hello everybody.
So how are you today?
I'm doing great today, and you?
I'm having perfect day today. Are you ready for the webinar?
Yes, I am.
Okay, and together with us on the line there is Oliver Felde from CFturbo in Dresden. Hello Oliver, can you hear us?
Hello, Luboš. I can hear you very well. And good afternoon to everybody.
Okay, perfect. The same question, how are you today?
I'm very fine, and I already heard that you also are very fine.
Yes,
Good.
we are.
Great.
So, are you ready for the webinar?
I am.
Okay, so very well. It seems we all are ready. So, hello again, everybody. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal pump from scratch in CFturbo software, and then how to simulate and evaluate it in turbomachinery CFD software. The webinar is being recorded, and its recording will be available on our YouTube channel. I hope everything works well. In case of any technical problems, feel free to contact us in the future, and we will gladly answer all your questions and comments. Please let me start with who we are and introduce us a little bit. So this is me. My name is Luboš Pirkl. I am co-founder and managing director of CFD Support. I am here with my colleague Radek Máca. Radek is our head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is senior manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms. About the program of today's webinar, so the webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be four parts in this webinar. In the first part, which is basically this general introduction. In the second part, let's call it the design part or CFturbo part, there will be a live example where Oliver is going to introduce CFturbo a little bit. And then he will show a live example of centrifugal pump design in CFturbo from scratch, with a final export of the designed model to the turbomachinery CFD. In the next part of this webinar, let's call it the simulation part or turbomachinery CFD part. There will be another live example where Radek is going to show you turbomachinery CFD simulation and evaluation of that centrifugal pump that was exported by Oliver from CFturbo in the previous section. In the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions to the special window below. You can also send us an email to info@cfdsupport.com. We will answer your questions later in this webinar. So feel free to put your questions. It's your time. This is quite important. It's your time. We are here for you. So just use your chance. Yeah, so let's start with the design part of the webinar. I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Okay, just briefly, CFturbo is a German-based company and has got 2 offices in Germany. One is in Dresden and one is in Munich. And we have also recently opened a US office, and that is based in New York City. Our main product is CFturbo, which is a conceptual turbomachinery design software, and it's dedicated to the design of any turbomachinery component you can think of, and it's based on latest design theory, very powerful, user-friendly, and so on. Right now we have something like 200 active clients globally, And we offer in our software suite different modules, and those modules are design modules for pump, which can both axial as well as centrifugal. We offer fans and blowers modules, compressors, turbines, stators that can be vaned or don't have vanes, diffusers, and of course volutes. And right now we serve those industries, and among them are the aerospace, automotive, home appliance, and so on industries. Okay, so that's quite quickly what I wanted to tell you about CFturbo, the company, as well as the program. But now I would like to give a short live demo, and to this end I'm going to transport my desktop into the web. Okay. Can you see my desktop?
Yes, we can. It's perfect, Oliver. You can go ahead.
Good. Well, so that's the GUI of our latest version of CFturbo. What you see when you start with a design from scratch is that gray desktop, and you see here immediately those four different kind of turbo machinery machines you can design. Because it's a pump session today, I'm clicking on that pump soft button, and the first thing I have to type in is the operating point at which this machine will run at the most time, or most of the time, because what we do always is a best efficiency point design. So the design point for this pump consists of a flow rate of 450 cubic meter per hour. It should produce some head of 30 meters at a speed of 1,800 RPMs. It's also necessary to define a fluid, because the fluid properties are also taken into account when we go through the design steps. Just for the CFD that might follow the design for validation purposes, there is also an inlet condition to be defined, and that's just one bar here. But in the design process, that's nothing which is considered, because we just take the pressure differences to make the design. Once I press OK, I'm asked by the program whether I want to carry on with the design of a radial or mixed flow impeller, an axial impeller, or a stator, or even a volute. I can start with a volute as well. Because the impeller is the central part of the stage, I'm going to start with the radial or centrifugal impeller. And the first design step is always to define what we call the main dimensions, and the main dimensions are just the inlet diameter, the impeller's diameter, and the outlet width. And one can do that by hand, by just telling or typing in directly the dimensions one has in mind, but one can also use the proposals made by CFturbo, and those proposals are based on different numbers, relations, and so on, which come from the turbo machinery design theory, and which are all implemented in CFturbo and can be accessed by clicking on that appropriate button. And just as an example, I'm going to show here the outlet width ratio, where the outlet width is given with respect to the impeller diameter. And you can see here that this is given with respect to the specific speed. And for the specific speed of 50, which is in accordance to our design point. A proposal would be to have a ratio like 0.13, and the source is Gülich's centrifugal pump book. And we have implemented a lot of those relations based on all the data that is publicly available. You can at any time change this number. You can also override our shipped databases. So everything is prepared to be customized by the user. Very important is to get an idea about the efficiencies you can reach. And again, they are given here, and they can customize. And once all the parameters are defined, one can use that calculate button in order to get a proposal for the dimensions, or one can also check this automatic checkbox, and then after every parameter change, you will see that the main dimensions are newly calculated. I will stick to the default parameters, and I will take off this button. And also what I want to do is I want to just want to get rid of this decimal places here. Okay, once I'm happy with the main dimensions, I can go further on to the next step, and that would be the design of the meridional contour. Here, everything is represented by Bezier curves, and I can grab control points, drag them around, and try to find a good design. In order to validate this design, there is a very rough estimate of the meridional flow implemented based on potential flow theory, and you can see here that where the curvature is high, you will get, of course, high acceleration. And after, again, every change of the contour, there will be an update of that flow pattern. You can also right-click on any of those control points and type in the coordinates you want to have, and that's what I did just with that impeller location. Once I hit OK, I get in the meridional view this kind of 2D image of it, but also I get a 3D impression of what we have designed so far. So that have been the first two design steps. The next step is to define and set leading and trailing edge blade angles. Especially the trailing edge angle is very important because that angle is responsible for the energy to be transported, or the head you want to reach. I want to have a freeform 3D shape of the blade. That's my first choice, and at the second tab I can again have CFturbo calculate the necessary blade angles, but I can also type it in by myself. So what we also take into account is some theory about the slip at the trailing edge, and one can also define a certain incidence if this is necessary. If I again click on that automatic checkbox, you can see what happened if I change the number of blades. So because the slip will get bigger after changing the number to a smaller value, the blade angle at the trailing edge is going to increase. Okay, I'll leave it on 5 numbers of blades, and nothing happened so far because that was only about the blade angles. But if I go now into the next design step, I can see in the preview how the blade would look like with a 0 thickness, like that. and I can again change mean lines by dragging around control points of this Bézier representation and can see immediately what happened in 3D, plus what happens on the relative velocity in the blade-to-blade passage on a certain mean surface. This again is based on potential flow theory, and it can help to find a good preliminary design. Once I'm happy with that, again, I can press OK, and now I see something in the 3D model, and the model now consists of blades with zero thickness, and because I want to have a certain thickness, I need to open the next design step, and here we have different modes about putting the or adding some thickness onto the mean surface, and that's the most simplest one. It's linear, but it can also be freeform, and again applying Bézier curves, and one can round the leading edge, and one can even incorporate some profiles from a built-in profile manager. But I want to stick to the simple case, which is the linear one, and I said OK, and in the 3D model it looks now like blades with very sharp edges, and that's why the last design step is the one where leading and trailing edge can be somehow shaped. So the leading edge, for instance, can have an elliptic shape, and very often the trailing edge is trimmed on the outlet. Okay, and by doing so, I'm very quickly ready with my first initial design of the impeller, and I want to save that and call it pump 1. But that's not a complete stage. It at least needs a volute, and to this end I'm going onto the outlet interface and add a new component, and the component is of course the volute. Again, the first step is to define the main dimensions, which are the inlet diameter into the volute as well as the inlet width of it. Again, there are some proposals made by CFturbo. Those can be taken or they can be overwritten. Next design step is to tell what is the general shape of the cross sections. We have implemented a couple of those, and they can be just trapezoidal, round, asymmetric, and so on. They can be also line segments, and with the line segments you can add some extra points, and by doing so you can just define any shape you want to have. It can be symmetric or not symmetric, so I could also have on the other side a different shape, and last but not least, I can also have a change of that shapes with respect to the rep angle. But again, I want to stick to the most simplest one, which is the round one, and want to leave it like that. Once I have chosen the general shape, I have to design the development of the size of the cross section with respect to the rep angle, and that's done here in the spiral development areas. There are different modes that can be chosen from. One is what we call the velocity-based one. Here we take the average circumferential velocity coming from the impeller, or it can be also just a geometric based one where the last cross-section is chosen either with its radius or with the area, and between the beginning of the spiral and the end there is a certain progression to be defined, which can be constant, linear, spline, polygon, and so on. Again, I leave it on the default, and if I now go to the 3D model, I see something what I would expect. Going back to the meridional view, make a fit, put a diffuser on it with a certain outlet diameter and a certain height, for instance 300 millimeter. It's very simple, and in 3D it looks now like that. And the only thing that is missing is the cut water here, and that's the very last design step for the volute. And here I'm choose one of the three design modes, and that one is the fillet mode, and I have to define a certain radius here. I can do again a preview here, and once I hit that button, I'm almost done when it comes to the design of the stage. What I want to show you right now is how to design a spinner rather than an axis design like it is done here. So because everything is fully parameterized, I can go back at any time to any of the design steps. And so I'm going back to the main dimension design step of the impeller, typing in a hub diameter of 0 in order to design this spinner here in the meridional design step. Very often you have the opportunity to right-click onto any of those active components, and a context menu will appear, and you have a lot of more functionality there. And I want to make use of the functionality of adding a contour of that in front of that Bézier curve. So that's one thing, and again another one is to be done here. And if I right click on the control points, I can type in the coordinates of that control point I'm interested in. So for instance, the connection point should be on 40 millimeter and maybe, let's say, 16 in radius, and it should be tangential, if that is possible. Yes, right now it's possible. And I also can give him a certain angle here, and then I'm already done. And if I go back to my 3D model, I now have a spinner here, and I can just place in front of the complete stage and pipe, and that's what I want to do. And the pipe should be a pure axial one with a certain length, so for instance 200 millimeter, and I can jump from one design step to the next just by using those icons here instead of pressing OK and choose it from the meridional view. So I go to the meridional design step, make hub and shroud straight, and that's it. Okay, what I also can do is I can have solids on hub and shroud at impeller and stator, and that's something I only want to show quickly. To that end, I'm going to to the meridional contour design step, tell him have a hub and a shroud contour, and here I can again right-click on it, split curves, drag control points around like that, split it again, put control points everywhere I want to have it, and maybe yeah, introducing or telling him exactly the position where it should go to. Okay, anyway, if I go back to the 3D model, I now have, I hope you can see it, a 3D representation also of the material solid given here. And because this is an initial design, it has to be validated by CFD, and that can be very conveniently being prepared by CFturbo. And so that's why I'm activating this CFD setup, which means it prepares everything for the design, for the CFD design. Once I'm pressing OK, I should see a segment like that. And I have to do something similar for the volute as well. Here I have to close that gaps, and if I want, I can also add a outlet pipe if I want. And if I go on the volute here, then everything is closed, and most of it is prepared for the design. Okay, last but not least, that has to be done for the stator as well. And in order to finish all the preparations for the design, I also have to do a final step, which is called solid trimming. And the solid trimming is a design step or a preparation step where by 3D Boolean operations, the solid is generated, and here one can also give radii at hub and shroud for the blades, and that's something I want to do. And once that is ready, I hope I can show that in the 3D model. And if I then make only that material domain visible, you see here that's the hub solid radius which I just defined. And if I switch off the volute, you can see what we have done so far. And my last step before giving the stick to Radek is to show how to make the design, the export for the turbomachinery CFD. And to this end, I open the export panel, choose all the components I want to put into the CFD model, give the one a name, have it saved somewhere on my computer, maybe change the parameters for the export. I want to change it to coarse in order to save a bit of time. And then I can start to export. And what is done is all the necessary geometric data, which are STL data with certain names, are exported together with a TCFD control file, which holds all the necessary information, including boundary conditions and so on. And that's it for the time being. And now I'm happy to give the stick to Radek.
Okay. Thank you, Oliver, for your contribution. Thank you for the turbomachinery design part in CFturbo software. It was very impressive. Thank you for it. It looks so simple to design such a pump. Okay, so the pump now was born. It was created in CFturbo, and now it's time to switch to turbomachinery CFD part of our presentation. So yeah, so let's continue with the simulation and evaluation part of this webinar. So let me give a brief description of what is turbomachinery CFD. So turbomachinery CFD is a unique software developed in Czech company, CFD Support. It is smart, it is easy to use, and it's very affordable CFD-Simulation tool. Turbomachinery CFD was designed for CFD simulations of all rotating machinery, such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, etc., both radial and axial machines, both compressible and incompressible fluid flows. It's based on OpenFOAM, and we believe Turbomachinery CFD is unique, at least for 4 reasons, so I will quickly go over them. So Turbomachinery CFD has, number one is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. What is paid for is the first delivery and technical support and the software maintenance. This gives the investment into Turbomachinery CFD a permanent value, of course. And also this means our clients can scale their CFD simulations in a really big way. Number two would be Turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final results report, it can be run by a single click or a single command, and all the process is being done automatically. For this reason, Turbomachinery CFD it's extremely effective. Number three would be we deliver extraordinary technical support. We are proud of it. We keep custom approach to every customer, to every issue. We never leave behind any of our clients, and we are very flexible in it. Technical support is unlimited, and we support our clients even out of the matters of turbomachinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. And the fourth one is the real tutorials are included in Turbomachinery CFD, which means the Turbomachinery CFD user has no doubts about the best practice settings. So there are included the real machines that are already preset. So user can basically take one of those tutorials, replace the geometry with his own. He can modify the settings and just run the simulation. The rest of the workflow is automated anyway, so the requirements on the user's CFD skills are very low when you use Turbomachinery CFD. So these are the uniquenesses. There are also many other benefits of using Turbomachinery CFD. I'm not going to go for all of them. I will only finish with my last point here, that here at CFD Support we believe the future of CFD is the automation. In CFD, everything can be automated, and the automation is extremely effective. It's even more effective than we expected in the first place. So nowadays, at CFD Support, we only think in automated sense, which brings a huge value to our users. Okay, so this was just briefly about Turbomachinery CFD. Now it's time for the live example of CFD simulation of the pump, which was created in CFturbo just a minute ago by Oliver. So now it's Radek's turn. So Radek, are you ready?
Yes, I am. So please hand me your presentation. I can start.
Okay, so it's your turn now. So let's get to the action.
Okay, so now I hope you see my screen.
Yes, yes, we can see your screen. So go ahead.
Okay, so hello again. This is Radek speaking. So I will directly start with the practical part, and during this part of the webinar I am going to show you how easy it is to work with our Turbomachinery CFD. So basically you can start already from scratch, but for now we have our work is very easy because we use the export from CFturbo. And using this export, it is even easier to run a CFD simulation and get the significant result. So I will start right now. So we simply start from the data which Oliver has just generated and exported. So I have here in the CFturbo from Oliver. And basically here there are just the input STLs. So it is the geometry, generated geometry in the STL format, and the configuration file. So the configuration file simply contains the important parameters for our software. Basically, it defines the simulation and it defines the geometry. Okay, so for the first computation, as Lubos already said, all is automated, so there is no need to change anything, and we can start directly using it. So to start working, you need just to click on the configuration file, and the new ParaView session with the TCFD setup will appear directly. So this is a standard, let's say, appearance of ParaView. In the left, you can see the pipeline browser in which the configuration file is already loaded. And to start using it, just click on the apply button. So now, as you can see, the layout button is split into two windows because our mesh, our geometry is already preset thanks to the CFturbo export. So now we can see the input geometry, and in the right window we can see all parameters which has to be set for the computation with its default values or with its preset values. So we have developed this graphical user interface directly inside the ParaView, which is a standard third-party software directly delivered with standard OpenFOAM. And directly here you are able to set the TCFD computation, so you can modify the setup, you can run the simulation, and also you can post-process the results. So it means that 100% of the workflow can be managed directly here in this GUI, and we provide both, of course, both Linux and Windows versions. So now I am working in Windows. So as you can notice here in the left properties menu, there are, or in this panel, there are several menus using which you can change the setup of the simulation. Basically, there is no need to change anything because everything is preset. So therefore, I'm going to make just a brief overview of this. So basically here in this general menu, you can load the preset TCFD file. You can save it, of course, and you have to choose which machine you would like to simulate. So in this case, it's of course the pump. In the coordinates, you just define the axis of rotation. In the geometry, there is parameters to scale the geometry because OpenFOAM works implicitly using unit meters. And for example, if CFturbo gives the geometry in millimeters, so we have to scale it. In the physics part, you simply define the fluid properties, and for pumps and water turbines, you can enable the cavitation risk, which at the end of the computation tells you the information about possible cavitation. So anytime you change anything, you should confirm it by clicking on Apply button. Well, the next menus, for example, turbulence, of course, you can change the turbulence model. Quite important part is the speed lines. So from CFturbo, you have this setup for one point, which corresponds to the best efficiency point. But if you would like to validate this best efficiency point, it is convenient to add more points or speed lines. But for pumps, usually the pump is designed for one rotation speed. So you should, for example, add computational points, and each point carries different simulation condition. So usually for the pump, we set the volumetric flow rate at the inlet. So for example, if the best efficiency point will be designed to this volumetric flow rate, so I would like to, for example, set different conditions to see if these conditions corresponds really to the best efficiency point. The same for the outlet condition, but there is a standard setup for incompressible cases, so zero kinematic pressure at the outlet. Okay, so this was the simulation condition, let's say. And I can go further. So in the simulation, there is important parameter processors. So you should change it with respect to your machine. And as Lubos already said, there is no limitation. So you can use any number of processor. Of course, we provide steady state or transient simulations, and you can change the numerical order first or second. Okay, and in the numeric there are some advanced parameters to change relaxation of algorithm, but there is no need to change anything in this menu. Initial condition here is just prescribed initial guess for the computation, and inside the components part there is defined the geometry. So our software generates the computational mesh automatically using SnappyX Mesh. And here you can define your geometry. So the strategy of construction of the computational mesh follows the construction of the design in CFturbo. So basically, the machine is split into 3 parts. In this case, so stator part, rotor part, and the green volute part. And each component is preset in this panel. So basically, you assign to each STL, you assign a type of the boundary, level of refinement. You can add boundary layers and the treatment at the interfaces. So there are 2 options: arbitrary mesh interface, or if this number is greater than 1, it uses mixing plane approach. So this is done for each component. And for example, what is important parameter is background mesh size. So for example, if you would like to increase the amount of cells in your mesh, so you should decrease this number. Okay, anytime if you for example, if you're starting from scratch, sorry, and generating your own geometry exported not from CFturbo, so it is useful this figure which tells you the topology of your mesh. So anytime you change anything, it will appear directly here. So it's really nice when you constructing mesh from scratch. Well, other menus contains the meshing option. Basically, it contains all parameters from SnappyX Mesh. In the post-processing, in the post-processing part, you can define here the interfaces, which is used for evaluation efficiencies, pressure drops, etc. So you will see it in the in the manager. In the report in a few minutes. And of course, scripting part, you can define your user-defined function. So anytime you are satisfied with your setup, so you should confirm it clicking on Apply button, and afterwards there is a special filter which is called TCFD Manager, and it is used to run the simulation. So I will enable it. And now in this left panel, you will see several buttons using which you can run the simulation. So basically, here is the output path where your simulation will be stored. You can define your own directory name in which the simulation will be stored. So I will set, for example, my case, and then I click on Write Case. So this process creates the standard topology. It creates all necessary files and directories to run the simulation. And afterwards, the case is saved. We are able to run the simulation by one click, this automatically run, or we can run the simulation step by step. So first create the mesh, generate the mesh. We can separately build each component, or we can mesh all components at once, and afterwards we can run the calculation. So I will click on the Run All, and you will see the progress. So at the beginning, the component 1 is meshing, and it continues in this way. So if I jump in time, so here I have, here this case I ran before the webinar started. So as you can see, all meshes is generated because these menus are green, and here you can see the progress bar. So for example, this simulation contains 7 points to be computed, and now the last point is computed, and you can see the guess how time does it take to finish the simulation or to finish each point. Anytime during the simulation, you can update the report. So it means you can see the progress of the simulation anytime, not only at the end of the simulation, but anytime during the simulation. And it will appear here. And anyway, at the end of the simulation, this report appears automatically. So you can see it right here in this panel, so directly here in ParaView, or you can go back anytime to the case in which your case was computed. For example, here in my computed case, and there is a directory report, and here is the report in HTML format. So anytime I can open it and see the results. So I will go just quickly through it. So in the first block, there is the overall information about the simulation, like machine type, number of points, mesh size, and other useful information. For example, this case I run on our cluster on 24 processor, and all points take just 7 minutes to compute. Here you can see the residuals during the computation for each point, and the flow rates during the simulation. Then there is several parts in which you can find the information about the given parameter or given variable, which is automatically evaluated. So for example, first is the head, and you can see here in the left, you can see the list or the table of the values for each point. It means the initial condition or inlet condition and the head for this point, and all is plotted in this figure. And in this figure, you can see the convergence process of this variable or of this parameter. And the report contains many of these parameters. So important one is the efficiency. So as you can see, the point number 4 with this flow rate is the best efficiency point. So you can clearly read from this figure how your machine behaves for each condition. You can see the efficiency progress again, torque for each point. Again, all is plotted in the figure and in the figure of the convergence process. Total pressure difference at the inlet and at the outlet. Total pressure per interfaces, so we can check the pressure at each interface. It means at the inlet to your geometry, at the interface between, for example, inlet pipe and the rotor part, and so on. And another bunch of information for velocity magnitude per interfaces, circumferential and meridional angle, so you can check the angle of attack into the rotor, for example, or the values of angles. And because we have enabled the cavitation risk, so we can see here the cavitation risk in percentage of the volume. So this is the first information about the cavitation. So we can see that for the largest head or the lowest flow rate, there appear cavitation. So the largest cavitation has 0.01% of overall volume. So this was the report, which is automatically generated, and let's say these are the information in written form. But anyway, anytime you can use your own visualization. So if you go to the case and click on this case foam, so new ParaView will appear, and directly inside you can visualize what you want. So I have prepared few visualization images or examples. So here you can visualize overall geometry, for example, with pressure distribution. You can visualize just a part, any part of the machine with, for example, total pressure distribution. You can make any slice with the glyphs or with arrows of the flow, which is directly fitted to this surface. And for example, you can also visualize the streamlines in any part of the domain. So you can use any filters which are implicitly in the paraview. For the turbo machinery, we have developed another useful filters. So first one is, for example, meridional average. So you can see the average on the axis symmetric parts, for example, on the wheel. So you can see nicely the pressure drop on the wheel. You can also use the filter turbo unwrap, which shows you blade-to-blade view. So, for example, you can see the pressure distribution at the blade-to-blade view, or you can also create the slices between hub and shroud. So, in a given percentage, so at a given radial coordinates, and on this slice you can again evaluate what you want. For example, the streamlines with the pressure distribution, so you can check the angle of attack and so on, if there is some recirculation or any other parameters. And last but not least, what I would like to show you is, for example, the cavitation risk. So there is a field which is called cavitation and holds the information in which cells the cavitation may occur. So, for example, this is the result for this flow rate. So I can skip between points to see for which setup the cavitation appears. So this is nice visualization of the cavitation. So maybe this is the last thing I would like to show you. So maybe my time is up. So
Okay.
So just to conclude, so as you have seen, the TCFD is a great and easy to use and powerful weapon for the detailed evaluation. You can evaluate always anything you want, and basically the process is really simple. In CFturbo, you design your machine, and then by few clicks, even without any deep knowledge of CFD, you are able to validate your geometry. So you just quickly generate the STLs and the configuration file in CFturbo, and by few clicks you are able to run the simulation and see the first results without any need of modification. So I believe that using CFD for turbo machinery evaluation has never been easier in this way. Oh, okay, well my time is up, so I have to hand the presentation back to Luboš. So Luboš, are you ready?
Okay. Yeah.
Perfect.
So thank you, Radek, for your live example of the TCFD simulation of the centrifugal pump what has just Oliver designed in the CFturbo. So I will take the presentation back to me. Okay. So yeah. So this was the TCFD live example, which brings me to the Q&A session. So now it's time for your questions and our answers. So please put your questions if you have one. We will get to it. And before we start answering your questions, we have a simple poll about your interest. So I'm gonna start it right now. So we would like you to vote. We would like you to vote. What is your interest? What are you currently interested? So whether it is CFturbo or whether it is turbo machinery CFD, or whether it is both, like a complete workflow. So please do give us your vote. So make your vote right now. I will keep this active for a couple of seconds. So we are obviously very curious on your preferences. So let's wait another, let's say, 10 seconds. So 10, 9, 8, 7, 6, 4. Okay, so last few seconds. So make your votes. Make them, and I stop it. 3, 2, 1 right now. So I'm closing right now, and also I will share the what are the results. So I can see 30% of people are interested in turbomachinery design and CFturbo, 26% are interested in TCFD, and also 44% is interested in both, which is very important for us. Okay, thank you for this. I'm going to hide this poll. Thank you for it. And let's get to the Q&A. So what we have here. So do we go one by one? Okay. So what meshing tool have you incorporated to the mesh your geometry? Thanks, from Milan Sekularat. So will you, Radek, may I ask you to answer this? Which meshing tool do we use here?
Sure. Yeah. We are using standard snappy hex mesh. And with the preset values, let's say with best practice values. And I hope you hear me. Yeah, perfect. So this is the type of the mesh which snappy hex mesh generated. It's standard hexadominal mesh. It's unstructured mesh, but it can mesh almost any type of any shape, and it is really robust. Yeah, it is not so nice like a structured mesh, but this is really useful, and our experience with this type of mesh is very well. So yeah, we are using standard snappy hex mesh tool for meshing. So, and the whole process is automated with respect to the CFturbo export with the given parts of the geometry and so on. But anyway, if you need to modify it to your needs, you are able to do it with these settings. So you can basically change anything, any parameter in snappy hex mesh using these menus on the left.
Okay, another question. Thank you for this, Radek. Another question of this kind: where to define fluid properties?
Oh, sorry, I didn't. Okay, so I didn't share my screen, so it was a mistake, I guess. But
okay.
I show some. Okay,
it's okay. We have had to. So another question of this kind: where to define the fluid properties from Taha?
Okay, I can show it. So I don't know if you see my screen now.
Yes, we do see it. Yeah.
Perfect.
Yeah, go ahead.
So I will go to the settings part, and here in the physics there are fluid properties. Yeah. So basically, dynamic this is incompressible case for the pump. So there is defined dynamic viscosity, reference density, and reference pressure for the evaluation of some parameters. Yeah. So here, basically, the important one is the dynamic viscosity and the reference density. So the fluid properties are defined here. So I hope I answered the question.
Okay, so yeah, there are so many questions. By the way, it's full. I mean, the room is full, so nobody else can come.
Go because I see a few of them to be answered very quickly.
Yeah. Okay. So yeah, another question: is it possible to include the leakage passages in CFturbo from Farzam? So I guess this is the question on CFturbo. So Oliver, may I ask you to answer this?
Yes, I can answer that very quickly. It's possible. It's just another option you have to set in the global setup in the main dimensions, where you can say whether the impeller has to be shrouded or not. So I can. It's just
Oliver,
a click away.
Oliver, do you want me to switch the presentation to you?
Yes, that would be nice. Yeah.
Okay. So I'm making you a presenter right now.
Okay. Do you see the
Okay, now,
screen?
yeah, we do. Yeah, please.
Okay, so quite simply, go back to main dimensions to the first tab, and there is the checkbox unshrouded. And if you check that, you can type in a certain gap between the casing and the blades. So I'm going to make that a bit bigger because then it's easier discernible. And if I click OK, I hopefully get an update of the 3D geometry. Clicking on default, and now there is a gap between, well, it's probably better if I just, there's a gap between, I hope you can see it, between the casing and the blade. Okay. That's all from my side.
Okay, thank you, Oliver, for this contribution. So yeah, we have so many questions. So we have to make a deal at what time we stop. So let's give it 10 minutes, let's say. So we are going to stop at about 10 past 4. So okay, so there are so many questions. So for example, this which formats like STEP or I just of TurboMachinery CFD software can support from Saresh question. Yeah, so I will quickly answer this. We currently, the TurboMachinery CFD supports only STL format. So it's so simple. Only STL. It's stereolithography. It's very standard. Almost all preprocessors or CAD systems can export in STL. So we stay with STL, and yeah, so it's just the STL for now. Which turbulence models are available? The question from Taha. So again, quickly, currently in the user interface, there's K omega SST, K epsilon, and laminar for various tests, and those are just in the graphical interface. Of course, TurboMachinery CFD is fully compatible with standard OpenFOAM. It's 100% compatible with standard OpenFOAM, so you can put your own turbulence models very easily. You can, for example, you can write the case down on the disk, and then you can, for example, change the turbulence properties and run the simulation this way, or you can use a script, a Python script, very easy, very simple. Okay, well. Where to define it? It's answered. Where do you obtain your predictive values? For example, B2 over D2 versus specific speed, and are there a good estimate? Be better to provide a value instead. From Dustin. I guess this is a question on Oliver again.
Yes. Well, again, CFturbo is based on turbomachinery design theory, so we solve some balance equations, but in order to make a good initial design, we not only, or it's not only enough to have these balance equations solved, but you also need this information about some relations, about some similarity numbers, and those are taken from all available sources you can imagine. So for instance, if I go to our approximation function on the hydraulic efficiency, again, there are curves given with the volume flow as a parameter and with respect to the specific speed, and all these things are publicly available. The sources are also always shown there, and some of them might be based on our own experience, but most of them are from textbooks, from papers, and so on, and the references are given within the software. And the last word on that, if you feel that your experience is different and you might have curves that have a different shape, at any time you can add your own stuff here, incorporate it here, and use it, and it will still stay with you on your desk, and you don't have to share the experience with us, for instance.
Okay, thank you, Oliver, for this. So Okay, Radek, so please go ahead.
So I will answer a few questions that I saw. So for example, what is the quality of the mesh, orthogonal quality and skewness? We told ask this. So these information are included in this report, and here are the details in the mesh. Okay, I should show my screen. Okay, I hope you see it right now. Okay, so here, Bosch, do you see my screen?
Yes, you do.
Perfect,
Yeah,
perfect.
please go ahead. Yeah.
So mesh size. In the mesh size, if you click on detail, you will see the details of each mesh part. For example, non-orthogonality with maximum 64. So the limit, let's say, for the rate computation is 70 in the SnappyX and for OpenFOAM. So all informations are here. Question about Y plus. Here is the, let's say, the maximum value and in overall mesh. But if you click in details, you will find the minimum, maximum, and average values for each part, for each STL, for each part of the geometry. So you can see that because we are using K omega SST standard wall function, so the values should be less than 300 and higher than 30 or 40. So basically, we are in this range. So the details can be found here. And if for your particular geometry it is not okay, so you can change the setup for the meshing. Okay, and there was other questions. Now, where is my question? Here. Yeah, right. And there was a question about the efficiency 0.89. Isn't it too much? I guess it is not, because it depends on the pump, and it can be seen that the CFturbo is a really nice tool, and you are able to
yeah
to design really high efficiency pumps.
Yeah, so efficient already. Yeah, it's not needed. But don't tell anybody.
Could you present some screen of the mesh? So I already did, I hope. So for example, this is the mesh for the rotor part. So you can directly visualize it in ParaView. And there was maybe one question regarding the hexadominant mesh. So hexadominant mesh, let's say the structured mesh with the hexahedras is the best for CFD, because CFD is based on finite volume methods, and finite volume methods really likes hexahedras and everything perpendicular to each other. So hexadominant mesh are convenient for CFD simulation using finite volume methods. Okay, so
another question: is it possible to multi-stage cascade stages? From Alistair. Question: actually, yes, it is. You can compute any number of stages. I think currently there is one condition you have to meet, which is the speed of rotation has to be the same for all the rotors and or for all the rotating parts or components. But I think we are working on this, and from the next version there will be, for example, the option for multiple speeds or for multiple rotating speeds of multiple components at the same time. But of course, multi-stage is possible. So let's check this question. Okay, yes, please.
Okay, I saw the question about the input of external mesh. So I will just quickly show that it is possible. If I go, do you see my screen? I hope. Bosch, could you check
yes,
it?
Yes, please. Yeah.
And here in the components where the mesh is defined, you are options to define the geometry using STLs or external OpenFOAM mesh. It means you can, because OpenFOAM provides a lot of conversions for a lot of external meshing tools, so you can convert it to the OpenFOAM and then load it directly here. So yeah, we have good experience with loading the external meshes, so yes, it is possible.
Okay, thanks. I think I see a couple of questions on CFturbo now. So is it possible to export the model to an external editor like SolidWorks? From Ellen. Oliver, would you go for this?
Yes, it is possible. There are some neutral interfaces implemented, which means you can export step IGES STL, but there are
And
also
again,
some...
I'm switching to you.
All right, okay.
Okay.
Okay, so I will go to the export panel, and that's probably the best thing to show. So again, neutral formats can be exported, which are given here. And these are IGES step STL and boundary representation. And if you want to use these interfaces, you have to configure your 3D view accordingly, and everything what you see in the 3D view is then exported. So that's one part, and the other part is if you want to go for certain cut specifications, they are given here. Like SolidWorks, or I think that was the question. Anyway, those data are point-based, and very often here macros are exported that can run into the proper CAD environment and can rebuild there the geometry of the stage. Okay, and Ljuboš, if you allow, I can also answer the next question, which is,
yes, please.
Can we give standard NACA profiles in CFturbo? That's possible to a certain extent, because what we have built in is a profile manager which have a couple of shipped NACA 4-digit profiles, some of the 65 series, and also some of point-based data, and those can be and those can be incorporated in the design step blade profiles. If I make the profile to freeform, maybe, and rounded, getting rid of the filling, then I can right-click on the profile I want to shape, and then I can say, okay, take a profile from our profile manager, and then I can choose from the built-in NACA profiles, for instance. I can generate new ones, and I can import some point-based one from Excel, for instance. But what you have to bear in mind, for the centrifugal part, or for the centrifugal modules, only the thickness defined by the NACA profiles is applied, because the mean line is, the camber line is already defined one design step before, which is done here. So yes, you can incorporate it, but it's only the thickness distribution that is applied.
Okay, thank you, Oliver, for this. And when we have you and your screen active, I would maybe I will point out the questions on CFturbo, which I saw. The one on there was a question on some surfaces, which I can't see right now. Anyway, in CFturbo, can you simulate surface finish, which is not very clear to me, but that's, would you?
I think that's probably there's some sort of a confusion. CFturbo is just a design package. If you want to simulate something, you should use a simulation package like TCFD. But yeah, so it's not possible because it's not in our focus.
Okay, maybe the fillets or something. But anyway, another question from Jussi Kangas. Hello Jussi, we've been in contact in the recent past. Hi. I would have a question for CFturbo. Overhanging volute design for air compressor impeller, basic design parameters and evaluation. How would it be done?
Overhang volutes is just done by, if I go to the meridional view and go to the volute, I can again choose the second design step, and here I would choose from the general shapes we have implemented. One would be the round asymmetric, and the other thing would be the around internal asymmetric, and that's what I just try to show quickly with a certain neck width. Maybe I'm doing that a bit bigger, and the ratio could be also a bit smaller. Okay, and if I press OK, then what you see here is there's some sort of intersection, so probably the round asymmetric would be the better choose, and it can be like that.
Okay. Another question perhaps for CFturbo is how can export the solid part of designed impeller from Majid?
Okay, yeah, that's again, I have to configure my 3D view to the part I want to export, and here it would be the let's do again a solid finishing. Here it would be just the solid part of the impeller. I have to do a solid finishing before that, and if I then make that discernible in the 3D view, get rid of all the other stuff which I don't want to see, for instance the hub, then I have the solid part here, and now I can use all the neutral export interfaces in a usual way. So just go somewhere, choose, for instance, I just do the export, and that's it.
Okay. So another question, could you present some screen of the mesh, which is, I think we had one. Can we give, yeah, this was answered already. Yeah. Are you able to export CFD pressure and velocity data to the neutral CGNS format for such subsequent processing for acoustic analysis using aeroacoustic sources? From Peter, yes, we have a converter, special converter of the results to CGNS format. As far as I know, it works. I'm 100% sure it works for volumes, but at the surfaces, I think the CGNS format is not fully compatible with OpenFOAM interpretation of, for example, boundary conditions, but for sure for volumes, and I think it's enough, and it's answering your question. So yes, we can. So it was this, and I also saw another important, yes. Hello, is it possible to import also other geometry, not from CFturbo, from Anna-Lena? Question. Yes, it is, of course. CFturbo is a great, easy to use tool for turbo machine design. But if from any reason you have your geometry already, of course you can import it in turbo machine CFD exactly the same way. You just provide the surface geometry and the configuration file, or you set up everything from scratch in turbo machine CFD, and you can simulate it. And of course you can also load external meshes from other CFD codes. So it's, in this sense, it's very compatible with. It's very open on both ends. I mean, you can import anything, and you can export in. You have many options in exports. So yes, of course. Okay, I think we have answered the vast majority of the questions. Yeah, so we are over time. So let's conclude. So I'll take the presenting back. I'll go back to my screen. So can you see my screen right now?
Yes.
Can you? Yeah, okay. Yes. Okay. So yeah. So it's time to conclude. This is it for today's webinar. So feel free to contact us in the future. I'm sure you know how to do that. The questions about the CFturbo are to be sent to CFturbo. The questions about turbo machinery CFD are about to be sent to CFD support, of course. We will gladly support you in your turbo machinery projects. it's our job and also a pleasure for us. Yeah, anything more to say? Oliver, would you say something?
Yes, I thank you for your audience, and I'm looking forward to your questions. Yes, feel free. Don't hesitate to contact us in case of any questions. Thank you. Bye bye.
Okay, and Radek, would you add?
Yeah, just I think let me say that I really believe that in the CFD field, our software and the synergy of CFturbo and TCFD is the future of turbo machinery virtual prototyping. So I really, yeah, it's really nice, and thank you also for the yeah, thank you the audience, and we are looking forward to the future cooperation.
All right, so we would like to thank you for your attention. We are looking forward to collaborating with you, so stay tuned and bye-bye for now. Bye-bye.